This lecture will be an introduction to Phasor representations. So, throughout electrical engineering, when we look at linear circuit analysis, frequently we find that excitations are sinusoidal in nature, and such a sinusoidal excitation, which is often in the form of a voltage signal, then has the general form given as Vt is equal to Vm cos omega t plus delta, where Vm represents the amplitude of the signal, omega is its angular frequency, and delta denotes the phase of this sinusoidal signal. So, study of circuits with sinusoidal excitation is an important aspect of circuit analysis. And when you do circuit analysis, what you are essentially looking at is differential equations that represent the circuit behavior. And to these differential equations, the input voltage applied is then in this form. More specifically, if you apply a sinusoidal input to a linear circuit, then after a sufficiently long time, you will find that the response of the circuit would also be sinusoidal. Right? This is one of the properties of a linear differential equation. So, the property is that a sinusoidal input would result in a sinusoidal output at steady state condition. And an important thing to note about this is that the frequency of the sinusoid remains the same for both input and the output. Therefore, if you now had a technique or a tool that would simplify the analysis of sinusoidally varying quantities and differential equations with such inputs, it would then be very helpful. And that is exactly what a Phasor representation provides. It is a mathematical transformation which makes our life easier when we are dealing with sinusoidal quantities in linear system analysis. So, let us then look at what the Phasor representation is. The whole idea of a Phasor representation is based on the Euler's formulation, Euler's relation, which says that e raised to j theta can be represented as a complex quantity cos theta plus j sin theta. That is all. The term e raised to j theta is called a complex exponential, and it has the property that its magnitude is always unity, and that is because cos squared theta plus sin squared theta is always 1, and the angle is the same as the angle theta. So, in polar form, this can then be represented as 1 angle theta. So, now suppose that I have a signal v of t which is given as Vm cos omega t plus delta. Then what I do is I define a new signal Vct, which is defined as Vm cos omega t plus delta plus j times Vm sin omega t plus delta. Right. So, this is a new complex signal which is defined from the original signal Vt, and this signal then according to Euler's relation can be represented as Vm e raised to j omega t plus delta. And so Vct is then a complex quantity, and so it can also be written in a polar form with the magnitude Vm and the angle omega t plus delta. Right. And so now, having defined this new signal Vct, I can get back my original signal Vt if I am given the Vct. So how do I do this? I can write V of t as the real part of this signal Vct. So the real part of the signal Vct is the same as Vt, and then I can represent it as the real part of Vm e raised to j omega t plus delta. Right. So notice what I have done here. I have essentially represented my original signal Vt in terms of a complex exponential signal Vm e raised to j omega t plus delta, and this is helpful because an exponential signal is often much more easier to handle than a sinusoidally varying quantity, and therefore instead of solving a differential equation with a sinusoidal input, which could be a difficult problem, one can now look at a more easier problem of solving an equation with an exponential input. So that is done by representing V of t as an exponential quantity function, and then what you do is you apply this complex exponential signal to the differential equation. Now it is easier to solve, and then you solve the differential equation and take the real part of the solution, and then that will give you the desired output which would appear if Vt is applied to the circuit. So that is the basic idea of using Phasor representation for solving differential equations. The idea is that you transform the equation to a complex exponential domain where it becomes much more easier to solve the equation, and then having solved the equation you transform it back to the original time domain by using this relation, this transformation relation defined here. So before going to the details of how we do that, let us pause and have a look at this new complex exponential signal Vct, which is defined as Vm angle omega t plus delta. So this signal Vm angle omega t plus delta is a complex quantity, and therefore we could try to see how it looks like when it is plotted in the complex plane. So the complex plane has the x-axis as the real part and the y-axis as the imaginary part, and then if you plot this Vct on the complex plane, it has a constant magnitude Vm. So you draw an arrow of length Vm to represent this signal Vct, and it will be drawn at an angle of omega t plus delta. Right. So when you do this, then the projection of this particular vector on the real axis, this length will then give you what is your V of t. So, that is the vector representation for the signal on the complex plane. And when I say vector, note that it is not a physical vector quantity like a displacement or a force or a velocity. Those are all quantities with a magnitude and direction when plotted in spatial Cartesian coordinates with the x axis and y axis as the spatial directions. Whereas the vector that we are looking at here is just a complex number representing a sinusoidally varying quantity, and it is a vector only when plotted in the two-dimensional complex plane. So, that is the difference between the conventional sense of the term vector as is used in physics and this term vector when we use it in complex notation. Also note that the angle that this vector makes with the real axis is omega t plus delta, which increases linearly with time. So, therefore, if you now look at the complex plane over a period of time, you will see that this vector will keep rotating as time progresses, and it would then trace out a circle in the complex plane, and the speed of rotation of this vector would be equal to omega, which is the angular frequency of the original sinusoidal signal. So, such a rotating vector in the complex plane is then called as a phasor. So, a rotating vector in the complex plane is called the phasor. And again, if I look at the signal VCT, I can write this signal VCT as Vm e raised to j delta into e raised to j omega t. It is the same as saying e raised to j omega t plus delta. So, you see that this signal VCT contains all the information about the sinusoidal signal. Vm represents the magnitude, delta represents the phase angle, and omega here represents the angular frequency. But as we have already seen in differential equations, when we try to solve these differential equations with sinusoidal inputs, the frequency remains the same for both the input and the output, right. So, what you can then say is that the information about omega is sort of redundant in the sense that we do not need to solve the equation to calculate the frequency of the output signal. It is already known that if the input has a frequency omega, the output will have the same frequency omega. Whereas, for the magnitude and phase you cannot say that. Those are quantities which you have to find out by solving the equation. And so, because of this redundancy of the term omega, when representing this phasor quantity, it then makes sense to omit the omega information, and conventionally therefore, the phasor is represented as a time invariant complex quantity by removing the e raised to j omega t part, and it is then represented as Vm e raised to j delta, or in polar form it is Vm angle delta. Right. So, therefore, we can say that the phasor V is simply a time invariant complex number. So, it is a time invariant complex number, or if you plot it in the two dimensional plane, it is no longer rotating, it is stationary, but that is just a representation of the phasor. And if you know this phasor quantity V, then you can always get back the complex exponential signal Vc as V times e raised to j omega t, which will transform it back to the rotating vector formulation. And therefore, if you know the vector, or if you know the phasor V, this is the phasor V, then you can calculate the time domain quantity also as real part of the phasor V e raised to j omega t. Right. So, what we have essentially done is we have reduced the representation of a sinusoidal signal to a simple time invariant complex number form, and then this should give us some convenience in dealing with sinusoidal quantities. So, let us start by looking at how this notation would be helpful when working with sinusoidal quantities. So, suppose that I have two sinusoidal quantities which I would represent as V1 t is equal to Vm1 cos omega t plus some delta 1, and V2 of t is another voltage input which is having some amplitude Vm2 and some phase delta t. Suppose that these two voltages are then connected in series, and you are interested in knowing the resultant voltage V1 plus V2 of t, right. So, the conventional or the straightforward way of doing this would then be to expand the terms cos omega t plus delta 1 and cos omega t plus delta 2 using the trigonometric relation. So, you can use the relation cos of a plus b equal to cos a cos b minus sin a sin b, and then what you would do is expand these brackets and then collect the terms containing cos omega t, and you will get a relation which would look similar to the right hand side of this equation. And so, then you transform it back to a form of cos a plus b, and ultimately you will get a result which would be in the form some Vt cos omega t plus delta t. So, this may be the result you get by the direct method using trigonometric formulas. So, I am not going to do that now, but I recommend that you try this out and see that you get a cosinusoidal signal with a certain phase and a certain amplitude. But now what we will see is how to do this calculation using phasor notation. So, what we can then do is represent V1t and V2t as phasors. So, V1t, if you represent it as a phasor, it is simply equal to the real part of say Vm1 e raised to j delta 1 e raised to j omega t, or let me use the phasor notation itself. So, this can be represented as V1 phasor into e raised to j omega t, and V2t can be represented as the real part of V2 phasor times e raised to j omega t. And therefore, now if you want to add V1 plus V2, the addition what you will do is the sum of these real parts. And if you are familiar with basic complex number algebra, you will recall that the sum of the real parts of two complex numbers is the same as the real part of the sum of the two complex numbers, right. So, using that relation, we can then say V1 plus V2 is equal to real part of phasor V1 e raised to j omega t plus phasor V2 e raised to j omega t. And since e raised to j omega t is common, you can do this as V1 plus V2 e raised to j omega t. So, look at what we have done. We have essentially reduced this summation of two sinusoids as simply the sum of two complex numbers. So, what you will then need to do to calculate Vt and delta t, which is the sum. So, we can represent it as Vt angle delta t would then be equal to the phasor V1 plus the phasor V2. So, essentially you will only need to add two complex numbers and convert it to polar form to find the magnitude and the angle, and then you can straight away write the sum of the two sinusoids as Vt cos omega t plus delta. Well, the advantage obtained by using phasors may not be very obvious from this example of addition of two sinusoids, but you can think about what happens if you have to add more number of signals. Let us say you have to add 4 or 5 signals, then the trigonometric method becomes terribly difficult, whereas the phasor method would then simply be equal to or simply reduce to addition of a certain number of complex numbers. That is how much benefit is obtained from doing this in the phasor form. And then now let us look at the analysis of a differential equation. So, let us first consider a simple RL circuit here and look at how we can solve this circuit by using phasor notation. So, there is an input voltage Vt which is applied to this RL network, and if you consider that Vt is again a cosinusoidal signal represented as Vm cos omega t plus delta, and then you could formulate the differential equation corresponding to this circuit as Ri plus L di by dt is equal to V. So, I and V are both functions of time, and then you can try to solve it. So, this would be equal to Vm cos omega t plus delta, and then you know that I is definitely going to be a sinusoidal signal of the same frequency. So, it would have some amplitude Im, and then it would have some phase which is represented by say phi. So, we will see how to solve this by phasor analysis. What we do, as I have said, is instead of considering this original equation with a sinusoidal input, we consider a modified equation where the input is equal to Vct, which is the new signal, complex signal what we have defined. So, in that case your current would also be a complex quantity, and then you can write it as Ric plus L dic by dt is equal to you can say it is Vm e raised to j omega t plus delta, and your Ic is the complex exponential current which would be Im e raised to j omega t plus phi. Im and phi are the two unknowns that you would like to find out by solving the equation. So, in this case let us see what this reduces to if I substitute for Ic. So, if I substitute for Ic in terms of this complex exponential, then I get the equation R into Im e raised to j omega t plus phi plus L into, now here we have the derivative of this complex exponential, and the derivative of an exponential signal is another exponential signal. So if you take the derivative of this, you will get L into Im into j omega times e raised to j omega t plus phi, and this would be equal to Vm e raised to j omega t plus delta. Right, now you have an equation which does not contain any derivative terms. It is a complex equation, and further advantage is gained by noticing that you have an omega t term common in all of these equations. So you can cancel that out, and all you are left with then is r Im e raised to j phi can be represented as angle phi, plus then you have a j omega L Im, and again angle phi would be equal to Vm angle delta. So this now is just a complex algebraic equation. So the differential equation has been reduced to a complex algebraic equation, which you can easily solve for to find out phi as well as Im. So how will you do that? This can be represented as r plus j omega L into Im angle phi equal to Vm angle delta. So by comparing the magnitude part and the angle part, you can get both Im and phi. So Im would be Vm by magnitude of r plus j omega L, and if r plus j omega L can be represented in polar form as z angle theta, then we can write this equation as z Im angle phi plus theta is equal to Vm angle delta, which would then give you the relation phi is equal to delta minus theta, and theta for this complex number would be tan inverse of the imaginary part by the real part. So this then gives me phi as delta minus tan inverse omega L divided by r. So the advantage we have gained here by using phasors is that the differential equation was reduced to a algebraic equation in complex variables, which will directly allow us to calculate Im and theta. And the same method can now be extended even for any other complex differential equations. All you have to do is replace the input with the complex exponential, and automatically the derivative terms will disappear, and you get this algebraic equation in complex variables. And before we stop, let me also plot this function in the complex plane, and not the function, the voltages and currents. So the voltages would be with a magnitude Vm and at an angle delta as we have taken them, and the current, if you plot it, it will be at an angle Im and it will make an angle phi, and as we have seen, phi is delta minus theta, so theta is then delta minus phi, so this angle would then be theta. And then this then represents the phase relation between the voltages and currents, and often it is the angle theta which is of interest to us, because delta and phi are not properties of the system. It depends on what time instant you observe the sinusoid. So delta and phi therefore are not very important, and it makes sense to look at the angle between Vm and Im, and therefore often while drawing a phasor diagram, what we do is we take one of these quantities as the reference, say Vm as the reference, and then plot Im making an angle theta. That's all the information that we need in drawing the phasor diagrams. Right, so these methods can be extended even to circuits containing R, L and C in different fashions. So I will request you to try solving some of these circuits and understanding for yourself the benefits offered by phasor representation. So I will stop for now. Thank you.